We have finished the study of electrostatics. Now we will start the study of steady electric currents. Now we know that the motion of charges or the charges in motion create current flow. Now there can be several types of current, like convection current, conduction current, electrolytic current. Now conduction currents are usually found in conductors and semiconductors. Convection currents are usually found in vacuum or rarefied gas, that is equivalent to vacuum only. And electrolytic current refers to the flow of ions and charge carriers, is usually in a liquid, like in the process of electrolysis. Now, usually conduction currents are because of the drift of the charge carriers, which may be electron, hole, and or means either one or both. Like for semiconductors, both electron as well as hole drift to create conduction currents. Now we might have heard about Ohm's law, but we will see that not every kind of current or every material follow the Ohm's law. There will be different laws which will be followed by with the various kinds of current. We will also see that the governing equations, especially in homogeneous conducting media, is very similar to the Poisson's and the Laplace equation. And so the solutions formed by these steady electric currents, the form of solution which we will find will also be applicable to the solutions of electrostatics. So in all times when the numerical methods were not that much developed or computers were not so much sophisticated to do numerical calculations easily, at that time what people used to do, they used to solve a similar kind of problem in steady electric currents or DC currents, and they used to find the form of the solutions practically. And since the form of solution for electrostatics would have been similar, so in that way they used to verify or find the solution for the electrostatic problem. And what they used to do, they used to create a voltage or potential difference by putting electrodes in an electrolysis tank, and that tank used to have a poor conductivity dielectric or solution, and because of this that electrolyte used to decompose into oppositely charged ions by the electrolysis process. And with the proper geometrical shapes of various electrodes, they could easily evaluate various geometries or simulate the various boundaries in electrostatic problems also. So by doing experiments in this electrolytic tank, they used to find the solution for electrostatic problems, just because the governing equations are very similar or same in form. So this is one of the examples where you are not able to find the solutions analytically, you find the solutions experimentally. Now convection currents, these are because of the motion of positive or negatively charged particles in a vacuum or rarefied gas, like earlier CROs, cathode ray oscilloscopes. And in thunderstorm, there is usually a violent motion of charge carriers, especially electrons. So that is also an event of convection current only. And it is because of the hydrodynamic motion which causes the mass transport of charge carriers. And this is not being governed by Ohm's law, which we already know and we might have studied earlier also. There are different mechanisms which are involved here, which is different than the mechanism for which Ohm's law is valid. And the mechanism of conduction current is different from the convection current as well as the electrolytic current, which I just described earlier in the case of electrolytic tank. So in this way, we can expect that the governing equations will be different for the conduction current as compared to convection or the electrolytic current. Now, in this lecture, we will try to derive some equations for convection current, and we will verify that these are not equivalent to that of what we call as Ohm's law. So what is that? Let us see the scenario. Earlier, when there were no semiconductor diodes, or even now for some special applications where the solid state semiconductors are still not have reached to their rated values, Still, some vacuum tube diodes are used, and in earlier they were used so frequently. So what used to happen in them? There used to be, let us say, two oppositely charged plates. This is, let us say, is charged at plus V, and this is at ground potential, and this was called as anode, and this was called as cathode. Now this was heated, so that due to heating there occurs thermionic emission. That is, electron is ejected because of heating, because it gets energy, and that energy is greater than the work function, so it gets ejected from this. Now, because there is a field setup between these plates, this electron will start to move towards this plate. So by controlling the motion of this electron or the charge carrier, we could control the characteristics of this device. Now we are going to assume that there is a space charge near this cathode, because electrons are being ejected now, and these electrons, because there is no reversal in polarity, are not going to easily get intermingled or get discharged. So there is a uniform space charge, but we are going to assume that this space charge is limited in its volume, so that it is not covering the whole area of this device. Only very small portion near this cathode is having space charge. So because of this, what is going to happen, we are assuming that this space charge is going to create an opposing field. Because of this, the electrons which are just coming out of the metal of this cathode are having an initial velocity of 0. That is just they are just starting at initial velocity of 0. And furthermore, since we know that this potential is also 0 because we have grounded it, so we know the two conditions, that the initial velocity of the electron is 0 and the potential. And now let us say this is y-axis and this is x-axis. So this is positive AY direction. So E at 0 is equal to AY EY 0 equals to minus of AY dV y over dy, because we are assuming that this symmetry is there, and we are neglecting the fringing effects and everything. So only variation with y will be there in the potential. That's why we are just using this term. And we know at y is equal to 0, here y is equal to 0, and here y is equal to d. This is equals to 0, because net electric field is 0 because of limited space charge here. So we have assumed, and this assumption has given us this boundary condition. Now in steady condition, when everything is running for some time and steady state is reached, then we know that there will be a constant current density, like electron will boil off from this cathode at a uniform rate, and they will reach at a uniform rate to the anode. So the current density is going to be uniform, and since electrons are going to be from cathode to anode, so the current direction is going to be from anode to cathode, and we have taken positive y direction from in this direction. So current density is going to be negative y direction, and it is going to be uniform. Let us say it is AY, some charge density in this space. Since I already assumed that the space charge is very small and it is limited, so I'm going to assume that this whole space is having a uniform, if not uniform, a charge density which is varying with y only. And this is actually a negative quantity, uy. Since we know that electron is going to move in this field and it is going to accelerate or something, so we expect that the speed of this electron is going to be a function of its position along the y-axis. Now, if rho is the charge per unit volume, and if I multiply with this velocity, it is going to give me the current per unit surface area. So ampere per meter square is the unit, and this is called as the current density. Instead of cross, it is just multiplication by a scalar, and this is the vector. So this is going to give us a vector, and this vector is known as volume current density, or simply current density, and its unit is ampere per meter square. Now, current passing through a surface area, let us say if this is the current density vector. So current passing through this area is actually be given by the dot product of this area, because only the component which is perpendicular or parallel to the normal of this surface is going to pass through this. The other component which is parallel to the surface, that is not going to pass through the surface. So the current is what passes through the surface. The charge passing through a surface per unit time is called current. So only the component which is along the normal of this surface area is going to give us the current. So this is what we should remember. Now we will apply Newton's second law on the electrons or the charge carriers, and we know that the velocity u will be given by uy ay, where ay is in this direction. So using the second law of Newton, we can write it as minus EEY, where E is equal to 1.602 10 to the power minus 19 coulomb. That is the magnitude of charge on an electron, and minus E is a negative quantity. E is a positive quantity, but minus E is a negative quantity. And I can write it as E into minus of dVy by dt equals to E dVy by dt. Now I can write du by dt as du by dy into dy by dt by just using chain rule, and dy by dt is again equal to u. So we can write m du by dt equals to mu du by dy. So it implies this is equal to E dV y by, sorry, this is dy. The electric field is dV by dy. I by mistake wrote it as dy by dt. We should remember this, that this is special variation of voltage. So this is dVy. Now this mu du by dy can be written as the differential of, or d by dy of half mu square. We can verify this. It is equal to m twice of u du by dy. So this is the same thing. So in next slide we will continue, and we can write it as d by dy of half mu square equals to E dV by dy. On integrating both sides, we will have half mu square is equal to EV plus some constant C. Now at y is equal to 0, both v is equal to 0 and u is equal to 0. It implies the constant is equal to 0. So half mu square is equal to EVy. So this is first equation which we have got, or u is equal to under root of positive under root 2e by m v y. Now we need to find Vy in the region between these two electrodes. So we must solve the Poisson's equation, where the charge density should be expressed in terms of the potential between the inter-electrode region. Because there is charge inside between these two plates, we cannot use Laplace equation, so we will use Poisson's equation. Now we know that J is equal to minus rho u. So it implies rho is equal to minus J over u, and we know that this is the value of u. So we can write rho is equal to minus J under root m by 2e v power minus 1 by 2. Now from Poisson's equation, d2v by dy square is equal to minus rho by epsilon naught. I can write it now as J by epsilon naught m by 2e v raised to power minus 1 by 2. Now, although this equation appears to be formidable and very difficult to solve, But we can solve it by integrating and making it a complete integral, and we can make it a complete integral if we multiply both sides by 2 dv by dy. So I have multiplied both sides by dv by dy, 2 dv by dy. Now this will become a complete integral of dv by dy squared. We can verify this again. This is going to be 2 dv by dy into d2v by dy square, which is same. So this is equal to j by epsilon naught some constant 2e v power minus 1 by 2 dv by dy. Now we will integrate both sides so that this goes out. So on integrating and solving and putting that at y is equal to 0, y is equal to 0, v is equal to 0, and e is equal to 0 is equal to dv by dy. So the constant of integration will be 0. We will find that v raised to power minus 1 by 4 dv equals to twice of, it is very easy to solve now, j by epsilon naught m by 2e raised to power 1 by 4 dy. Now we will again integrate the left side. So on integration we will get 4 by 3 minus 1 by 4 plus 1 is equal to minus plus 4 by 3 v naught power 3 by 4, and we are going to integrate from dv is going to be integrated from 0 to v naught, where v naught is the potential of the top electrode or the anode. So this is going to give us twice of j by epsilon naught m by 2 epsilon naught 1 by 4, and the right hand side dy is going to be integrated from 0 to d, that is the spacing between these two electrodes. So you see that from this equation the current density magnitude is given by 4 epsilon naught 9d square 2e over m v naught raised to power 3 by 2, where v naught is the potential across the electrodes. So you see that this is not equivalent to Ohm's law. This equation is called as Child-Langmuir equation, and this is valid for the assumption where we have assumed that the space charge is limited and the electrons are boiled off at initial velocity of equal to 0, and the electric field is 0 at that point. This is a non-linear relation between the current density and the voltage applied between the plates. However, Ohm's law, which we will study, is a linear equation, but this is not a linear one. So you see that this is not Ohm's law. So we have seen clearly that conduction currents are totally different than the convection current which we have just seen, and convection current usually do not follow Ohm's law. They have some other different governing equation, and that is totally different from the conventional Ohm's law which we study. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel and join our Telegram group, whose link is given in the description of this video.